Moment of inertia. Mass is a measure of inertia for a linear motion. So if an object that you are looking at is big and heavy, then that means it is going to be difficult for us to move it. If the mass is smaller, then it will be easier to move it. The rotational inertia is similar in concept to linear inertia, except now we are going to talk about rotation. So in this case, if you have a heavier object, then it will be harder to rotate it. If you have a plastic bat, which is light, it will be easier to rotate. So rotational inertia, which is also called the moment of inertia, is a parameter that is used to quantify how much force or torque it takes a particular object to start rotating. Rotational inertia depends on the total mass of the object, and it also depends on the distribution of the mass itself. Mathematically, rotational inertia is given by mass times the distance squared. So here's the point. Rotational inertia depends not only on the mass of the object, but where that mass is placed relative to the hinge or the axis of rotation. If the rotational inertia is smaller, less mass is located further from the axis. If the rotational inertia is bigger, more mass is located further from the axis. So let's illustrate this. So for different rotational inertias, so for example, if you have a pulley which is attached to a mass and the pulley axis is attached, two masses are attached further away. So we say it will have a bigger rotational inertia. And if we are able to move those masses from further out inwards, then we are going to say it has a smaller rotational inertia. What does that mean? In terms of spin, this one will spin slow because it has a bigger rotational inertia. This one will spin faster because it has a smaller rotational inertia. So when you're thinking about this, think about ice skaters. When they spin around, if their arms are extended, they spin around slowly. But when they bring their arms in, they spin around faster and faster and faster. Inertia sticks are also a really good example of rotational inertia. So when you rotate, so there are two pipes that are made out of the same metal. They have, if you weigh them, they weigh the same, and also they have the same length. But one of them is going to be harder to rotate, and one of them is going to be easier to rotate. On the inside of these, there are two masses, which makes it the weight of both of these sticks to be equal, but in this case, the lead masses are going to be further out at the edge, and in this case, the masses are going to be further in. So now my question to you is, which one will be easier to rotate, the red one or the blue one? Think about what we just learned. Absolutely. The red one will be easier to rotate because around this hinge, because they are placed close to the hinge. These ones will be harder to rotate because more mass is located on the outside. Now let's talk about rotational inertia for solid objects. So in order to explain rotational inertia for solid objects, let's consider three cases for a uniform thin rigid rod, one about its center, one about its one end, and the last one is when the rotational axis is at a certain distance away from one of the sides. So in order to find the moment of inertia of a uniform thin rigid rod about its center, let's first draw a rigid rod. And since we have to find the moment of inertia about its center, I am going to call my origin to be here, right? So this means that if the length of the rod is L, the total length of the rod is L, then this means this is going to vary from L by 2 to L by 2, okay? In this case, I know that the calculus tells me that the moment of inertia is going to be given by R squared dm, okay? Now what is this dm? This dm is a small volume element that I can look at. So let me suppose that this is my small volume element, dm, which is, say, located at a distance x from the center, okay? And the length of this dm is going to be, this length is going to be dx, okay? So now how do I use all of this information in order to calculate my I? Okay, So this is now a one-dimensional thin rod. In this case, I am going to talk about something that's called the linear density. So linear density is going to be defined as lambda, which is equals to dm over dx. And the total linear density, total, is going to be defined as the total mass of the rod divided by the total length of the rod. This implies I can rewrite this dm as lambda dx. And if I was to take this to be the total dm, it is going to be m over L dx equals dm, right? And this r will now be replaced by x. So my moment of inertia equation will change from I equals integration of r squared, it'll be x squared m over L dx if I was to place these values in here, okay? And my limit of integration is going to go from minus L by 2 to L by 2, okay? Now m and L are independent variables in this case, so they can easily come out. So I will have m over L integration x squared dx from minus L by 2 to L by 2. Integration of x squared dx is just simply equals to m over L x cubed over 3 from the limit minus L by 2 to L by 2. So if I was to plug in the values of L by 2 in here, I will get m over 3L, L by 2 cubed minus L by 2 cubed, correct? So I just plugged in the limits of integrations, and I'm going to have this bracket on the outside because these are multiplied with both numbers, right? So now I'm going to have this is equals to m over 3L, and 2 cubed can come out, so it'll be 2 cubed divided by that equals L cubed minus L cubed, which makes this into a plus L cubed, right? Which gives me 2L cubed m divided by 3 times 8L, right? This one goes away, we get a 4. This one goes away 2, and my answer is 1 over 12 ml squared. So going back to our moment of inertia equations, this is actually true, right? It's 1 over 12 ml cubed. It does have the same units, and so for a rigid rod about its center, this is the value for moment of inertia. So this implies that for my rigid rod, case 1, my moment of inertia equals 1 over 12 ml squared. Good. So this is my case 1 solved. So case 2, now it talks about the moment of inertia of a rod around one edge. So same rod, if I was to find the moment of inertia around one edge, that means I can put my 0 in here, and I can put my L in there. That means that my values are going to change slightly. This exact same formula will remain the same, but now that I'm doing the moment of inertia calculations, my I will be slightly different. So let's suppose that my dm is here, right? And it has the same dx, but this is going to be my x now. So I can rewrite this expression as x squared m over L dx. But in this case, my limits of integrations are going to go from 0 to L. Right? Ooh. I forgot to erase this, so I'm going to erase that. This means I can rewrite this as m over L integration 0 to L x squared dx, right? And that means I'm going to get m over L x cubed over 3, right? And the limits will be 0 to L. And that implies it's going to be m over L cubed over 3, right? L goes away, and I get 1/3 ml squared. Okay? So for case 2, my moment of inertia is going to be 1/3 ml squared. Notice that for case 1, this was 1/12 and this was 1/3, but they have the same masses and the same lengths. So the moment of inertia depends on where the axis of rotation is. Now case 3, it says, what if the angle of rotation, the rotational axis is at a distance h from one of its sides? So it doesn't tell me that this is x, but it's at a distance h from one of its sides. So in this case, for case 3, I'm going to redraw the same picture again. And I'm going to, instead of calling them around one of the axes, I'm just going to say the axis of rotation is at a distance, say, h from one of the axes. So I just chose this one to be my coordinate axis. So I'm going to call this 0, or I can call this one 0, and that will be h. So what is going to be this distance? Well, the easy solution would be, if this is the total length, I can call this as L minus h, right? So this is going to be my total L minus h, and I can call this one as my origin. So in this case, what will be my limits of integration? If I was to rewrite this expression, it will still be I equals x squared dm, but in this case, my limits of integration will be from minus h to L minus h, right? So it goes from here to here, and then it goes from here to here, right? Okay. So if I was to integrate these ones, what will I get? Well, I will get, I'm going to just plug in these values. I'll plug in the dm as well here. So it will be m over x dx, right? And that gives me m over L integration x squared dx from minus h to L minus h, right? That gives me m over L x cubed by 3 from minus h to L minus h, right? I plug those values in here, and I'm going to get m over L minus h cubed minus h cubed divided by 3. Okay, now we can open these because we know the formula for a minus b cubed, or we could leave it like this. But this is basically what the answer is going to be. Once you know what the h is and how far it is, you can plug that number in and actually solve for it. So the thing I want you to notice about each of these is that it's the same rod in each of these cases, but depending on where the axis of rotation is, the moment of inertia is going to change. It is not going to remain constant.